Welcome to an introduction to capacitors, where we'll explore the power of stored electric charge. We will cover the fundamentals of these crucial passive electronic components. A capacitor is a fundamental passive electronic component that stores electrical energy in an electric field. Think of it like a water tower, storing charge when there is extra and releasing it when the system needs it. Here you can see symbols and physical examples of polarized and non-polarized capacitors. Capacitors are built from two conductive plates, separated by a dielectric insulator. When a voltage is applied, positive charge accumulates on one plate and negative on the other, creating an electric field. Capacitors block continuous DC after charging, but they allow AC to pass as they continuously charge and discharge. Capacitance is the ability of a system to store an electric charge. It is calculated by dividing the charge Q by the voltage V, and its unit is the farad, or F. Since 1 farad is a massive unit, practical capacitors are measured in microfarads, nanofarads, or picofarads. Common types of capacitors include ceramic capacitors, which are non-polarized and ideal for high-frequency use. Electrolytic capacitors are polarized, offer high capacitance, and are used for low-frequency power applications. Film and tantalum capacitors are used for precision and compact high-capacity applications. Calculating equivalent capacitance is the opposite of calculating equivalent resistance. In parallel, you add capacitances to increase storage. In series, the total capacitance decreases, effectively increasing the distance between the outer plates. One application is power supply smoothing. Rectifying AC to DC creates a bumpy voltage, or ripples. A large electrolytic capacitor charges during the peaks and discharges during the dips, smoothing the jagged DC voltage into a steady, usable line. Capacitors are also used for filtering and signal processing. Low-pass filters allow low-frequency signals through while shorting high-frequency noise. High-pass filters block low-frequency signals. Decoupling, or bypassing, uses small ceramic capacitors to filter out high-frequency noise spikes from power supplies near microchips. Capacitors are essential for timing circuits, using the predictable RC charge and discharge rate, such as in a 555 timer chip. They are also used for AC coupling, allowing audio and data signals to pass while blocking DC power voltages between circuit stages. In an LED fading circuit, the capacitor charges when the button is pressed, lighting the LED. When the button is released, the stored charge discharges through the resistor and LED, causing the LED to slowly fade out as the capacitor's voltage drops. To recap, capacitors store energy in an electric field and are vital for smoothing, filtering, and timing. Always observe safety warnings. Electrolytic capacitors must be plugged in with the correct polarity, or they may explode. Also, large capacitors can hold lethal charges for days, so always discharge them safely.